Welcome to my channel. In our discussion for today, we are going to discuss about the Laplace transform, but the Laplace transform of deriving the Laplace transform of cos at using the first principle. And by the first principle, the first thing that you need to understand is the first principle formula. The first principle formula, we know that the Laplace transform of a function f of t is equals to integration with respect to our limits exponential negative st we multiply by a function f of t, and our integration is with respect to dt. So when it comes to the first principle formula, this is how we write this is how we notate the formula. But we were told to derive the Laplace transform of cos at using the first principle formula. Now, at this step, we are going to say that the Laplace transform of cos at, because cos at is equals to a function f of t, is equals to integration with respect to our limits, the upper class limit and the lower class limit, exponential negative st we multiply by our function f of t is going to be equals to cos at, and our integration was with respect to dt. At this point now, the only thing that you are being required to do is that change cos at into an exponential, and by changing cos at into an exponential, we are going to apply the complex number formula. And by the complex number formula, we understand that exponential theta j is equals to cos theta we add to j sine theta. But when you check here in our working, the angle theta is equals to 80, to mean that exponential atj is going to be equals to cos at we add to j sine 80, to mean that at this point we can come and say that exponential atj is equals to cos at, or exponential atj is equals to j sine 80. But when we check our cos, in the complex number, cos is located on the real side, to mean that we are going to have our r here and have our r there. The sign, the j, stands for the imaginary. Now we are going to introduce our I there. Let us get back to our working, the function that we are working with. We understand that now the Laplace transform of a function f of t is equals to integration with respect to our limits, the upper class limit and the lower class limit, exponential negative st we multiply by cos at. Our cos at was equals to r exponential atj, and our integration was with respect to dt, was with respect to dt. At this point, we can come and factor out r because it is not a term of dt, because here we are integrating with respect to time. So here we are going to have the Laplace transform of a function f of t is going to be equals to r into the upper class limits and the lower class limit, exponential negative st we multiply by exponential atj, and our integration is with respect to dt. Let us now simplify whatever we are having at this point. By simplification of our exponential, when we introduce the laws of indices, we understand that when the bases are equal, we take one of the bases, and then since it is a multiplication, we are going to add the powers together. And by doing that, this is what we are going to have. The Laplace transform of now our function f of t is going to be equals to r integration with respect to our limits exponential negative s, we add to a j, and we come and factor out our term of t, and our integration here was with respect to d. From this point now we can carry out our integration, and by doing our integration we are going to have the Laplace transform of a function f of t is going to be equals to, when we integrate the exponential part here, we are going to exponential negative s, we add to aj t all over negative s, we add to aj. Since our integration was with respect to the limits, the upper class limit infinity up to 0, we also include them, and then we do not forget about the r, which stands for the real side. Now let us simplify whatever the function that we are having at this point, and by simplification and separation of function, and by simplification of the function that we are having here, we are going to have the Laplace transform of a function f of t is going to be equals to r all over negative s, we add to aj, we come and multiply by exponential negative s, we add to aj t, and our integration was with respect to our limits. Let us now do away with the limits, and by doing away with the limits from this function, we are going to have the Laplace transform of function f of t is equals to r all over negative s, we add to that into, here we are going to have exponential negative s, we add to aj, we come and multiply by the upper class limit, we subtract from exponential negative s, we add to aj, we come and multiply, we come and replace the term of t with the lower class limit. Now, by simplification of this one, we are going to have the Laplace transform of our function f of t is going to be equals to r all over negative s, we add to aj into exponential raised to a power of an infinity. We are going to have 0, we subtract from exponential raised to a power of 1. We are going to have here raised to a power of 0, we are going to have 1. By simplification of whatever we are having here, the negative sign is going to affect the size of the terms of the denominator. And by doing that, we are going to have r all over s, we subtract from aj. And this is how we go about simplification of whatever we are having within that bracket. At this point, we need to separate the real function and the imaginary function. By separation of the real function and the imaginary function, we need to do rationalization. And this is what I mean by rationalization. We are going to have the Laplace transform of our function f of t is going to be equals to r into 1 all over s, we subtract from aj. By rationalization, we are going to multiply both the numerator and the numerator and the denominator by the conjugates of whatever we are having here. So this is the conjugate s, we add to aj all over s, we add to aj, which is going to be equals to r into, on the numerator we are going to have s, we add to aj all over. On the denominator we are going to multiply the two. As we multiply by s, we are going to have a negative of s squared. We add to a j s. We take this one multiplied by that, we are going to have a negative of ajs. We are going to have a negative of a squared j squared. Now, from this point, we can come and simplify whatever we are having on the denominator. By simplification of whatever we are having on the denominator, we are going to have the Laplace transform of now a function f of t is going to be equals to r into s, we add to a j all over. Here on the denominator, we are going to have s squared, this one and this one. Those two terms will cancel out and we are going to have subtract from a squared j squared. At this point, we can do away with the j squared by saying that, by using the complex number formula, whereby j squared we understand is equals to a negative of 1. When j squared is equals to a negative 1, we can come and replace j squared here with a negative of 1. A negative of 1 multiplied by whatever we are having there. We are now going to have r into s, we add to aj. Everything is going to be all over s squared. This negative is going to affect the negative here, and we are going to have a positive of a squared. From this point now, up to this point now, we can separate the real function and the imaginary function. And by separation of the real function and the imaginary function, we can have the Laplace transform of a function f of t is going to be r into s all over s squared, we add to a squared, we add to aj all over s squared, we add to a squared. At this point now, we've separated the real function and the imaginary function. So how do we select that the real functions is now our answer? When we check at here, at this point here, cos at was located on the real side, to mean that at this point we can come and say now the Laplace transform of the derivative of Laplace transform of cos at now is equals to s all over s squared, we add to a squared. And this is how you go about deriving the Laplace transform of cos at using the first principle.